In this video, we're going to take a look at heat changes of state and also heats of reactions. We do that through heating curves, Hess's law, and standard heat of formation. So a heating curve shows temperature versus time for a given substance. How as you put more energy in over time, how the temperature of that substance changes or how the phase changes. The slope lines of a heating curve show the change in temperature for a given state, and then when it's flat lines, that's when we're in a phase change between a solid and a liquid or a liquid and a gas. So we see that here with water, from A to B, as time goes on, we put energy in, the ice is heating up all the way to 0 degrees Celsius. But then as you continue to put more energy in over time, that line is flat, where stays 0 degrees Celsius because the energy going in is causing the water to melt, the ice to melt. And then from C to D, again, we continue to put more energy in from there, and now the temperature raises from 0 all the way up to 100. Now we have 100-degree water, and then that evaporation, boiling process begins, and we have our water changing to water vapor or steam. And then once it's all changed to steam, again, now more energy will heat up the steam. So that's for just a given substance as energy is going in left to right, or if energy is coming back out right to left. We can look at energy in terms of a chemical process within a chemical reaction. One way in which we can calculate the amount of energy is Hess's law. So Hess's law is done by taking two or more smaller thermochemical equations and rearranging them in a way to then add them together and get one final equation that's made up of these smaller equations, and then adding the heats of those smaller equations to then get the amount of energy or the amount of heat that is released or absorbed for a larger reaction. Again, this is called Hess's law of summation, since you're adding together a bunch of smaller processes to get to the larger one. So the process in which this is done is by taking an equation, looking at these smaller equations and manipulate them to get to a larger equation. So find the substance within a particular smaller equation that is unique as it relates to the larger equation which you're trying to get to, and then you're going to manipulate that equation so it matches the larger equation that you're trying to solve for. So if you have a substance that you're trying to get into the right place and the right amount of that substance, and if it already is on the proper side reactant or product and it has a proper number of moles, you can just leave it as is and use it the way it is. But sometimes you don't have the correct amount of moles. You might have to double it or triple it or cut it in half, and then you're going to do that to the entire equation, to every substance within it, and to the amount of energy that's associated with it. And sometimes it's a reactant you need as a product, or a product you need as a reactant. So you can take that equation, you can flip it, and then if it's an exothermic process, by flipping that equation and running it backwards, it then turns into an endothermic, and vice versa. So let's take a look at how that process kind of all comes together. So I'm trying to figure out the amount of energy, the enthalpy change for this given reaction. When I have ammonia reacting with oxygen to make nitrogen monoxide and water. I'm going to have these three other equations in which I'm going to manipulate to then add together to get to my larger top equation that I'm trying to solve for. So we're going to look at that first equation on the top there and see how that relates to our large equation at the very top. So I have nitrogen, I have oxygen, I have nitrogen monoxide. Well, what in that equation is in my top equation that is also unique to it? So there is no nitrogen in that very top equation, so I don't need to worry about the nitrogen in this reaction. It also has oxygen, which is in that very top reaction, but if we see down in the third equation, there also is oxygen, so it'd be really difficult to try and figure out how the oxygens are going to fit together to get to that top reaction. However, my nitrogen monoxide that I have over there on the product side, there's no nitrogen monoxide from the second and third equations on the bottom there, so there's no way in which I add together these three equations and it comes from either of the other two. It has to come from that top equation, so therefore I need to get that to the correct side with the correct amount. So the good news is that nitrogen monoxide is already a product, which is what I'm trying to get as, but I have 2 moles of nitrogen monoxide being produced. In my very top equation there, I have 4. So that nitrogen monoxide we see right there, I need to double that amount so I can get to the proper amount of nitrogen monoxide. So I'm going to take double that entire equation. So now I'm going to take 2 moles of nitrogen with 2 moles of oxygen, and it's going to make 4 moles of nitrogen monoxide. And since I'm going to run that reaction through twice, well, it was 180.5 kilojoules released of energy to run it through once. So if I'm going to do it twice, I'm going to get twice the amount of energy back out. So double the amount of energy. It's going to be 361 kilojoules exothermic. Now I'm going to do the same process for the next equation. Again, it's got nitrogen, which isn't part of my larger equation I'm solving for, so I'm not going to have to worry about that. Same thing with the hydrogen, that's not part of that top equation, so I don't need to worry about that. But I do have ammonia, and again, it isn't either the first or the third of those equations, so the ammonia that is my very top equation I'm trying to solve for has to come from this equation here. So this one poses two problems, because the ammonia I have in this reaction is a product, but I need it as a reactant. And I'm also making 2 moles of ammonia, but I'm going to be using 4. So I'm going to have to take my ammonia, and I need to flip this equation to get it as a reactant, and I also need to double it to get the 4 moles that I need. So I'm going to double my entire equation. So now I have 4 moles of ammonia, and again, instead of being produced, they're going to be reacted, and 2 moles of nitrogen and 6 moles of hydrogen now being produced instead of reacted. And it was a negative 91.8 kilojoules of energy being released, exothermic, and now since I flipped it around, it's going to be endothermic, so that's a positive, and I doubled it, so now 183.6 kilojoules of energy being absorbed. So then lastly, look at this bottom equation. Again, I got hydrogen, which isn't part of that top equation, so I don't need to worry about it. I got oxygen, again, which is not unique to that top equation, because it's also in the top equation, the bottom one, that first one we used. However, this water is unique to this equation. It isn't in the first and the second ones on the bottom there, so the water that is in that very top equation has to come from this reaction right here. So if I make that match up, and then when I put all these together, it will all work out. So I have 2 moles of water being produced, but in my top equation I have 6 moles of water being produced. So I got to triple this equation to get the proper amount of water that I need. So now I have 6 moles of hydrogen reacting with 3 moles of oxygen to make 6 moles of water. So since I ran that reaction through 3 times, it's going to release 3 times the amount of energy. So 1,450.8 kilojoules of energy going to be released from that reaction. So now that I have those 3 different substances in the right amount where they belong, if I add these 3 different equations together, these 3 different processes all together, I get this much larger reaction of 2 nitrogens with 5 oxygens, 4 ammonias, 6 hydrogens, then making 4 nitrogen monoxides, 2 nitrogens, 6 hydrogens, and 6 waters. So that doesn't match my very top one. But if we look a little bit more closely, we kind of take a look at what's going on. Well, I have 2 nitrogen moles being reacted, and I have 2 moles of nitrogen being produced. So I had 2 to start and 2 to finish. That really didn't do anything, so I can eliminate those. And same thing with my hydrogen. I have 6 moles of hydrogen reacting, 6 moles of hydrogen being produced. So again, that didn't change from before to after, so that really didn't do anything either. Those are just spectating. So I can kind of cross those off and simplify this up. And now I see 5 oxygens with 4 ammonias reacting to make 4 nitrogen monoxides and 6 waters, which now does match that very top equation. So if adding these 3 processes together get me that larger equation I see up top, if I add together the energy associated with each of these processes, as we have there over on the right, and that will give me the amount of energy for the entire thing. So I find this entire reaction to be 1,628.2 kilojoules. Again, it's negative, so exothermic process. So that is a different way in which you can also find the amount of energy associated for a reaction. That's using standard heats of formation. It's kind of similar to Hess's law, but it actually breaks down a little bit even more, and then actually then, as it all comes together, it ends up being really simple. So we can look at the amount of energy associated for any given substance as it's being created from the elements that make it up. So if I were to react hydrogen and oxygen to make water, I know how much energy is associated with that reaction, because I can measure as hydrogen is combusted to make water how much energy is either absorbed or released. In that case, how much energy is released, again through calorimetry. So we use these standard conditions of 25 degrees Celsius in 1 atmosphere to then make the determination of the amount of energy, because it is going to change as those conditions change. And what they do is they figure out this heat of formation for these substances from their elemental state, and they do it by just arbitrarily setting the standard heat of formation for any given element as 0, because again, you can only measure energy as it transfers from one thing to another. So it doesn't really matter how much energy is there to start and how much there's at end. We're looking at how much energy is being absorbed or released. So that also works for the diatomic elements. So oxygen and hydrogen, like we just talked about with water, they too are also 0. So if those are my 0, and then I combust those and make water, measuring the amount of energy released as water is being formed will tell me, therefore, how much energy there is in water relative to their elemental state. So if those were starting at 10 and went to 20, or if they start at 50 and went to 60, it's going to be the same difference. So then we can take an entire table and put together all this information and use that information then to figure out the amount of energy being absorbed and released throughout the entire reaction. So we can find the total heat or energy of a reaction by taking the heat of formation of the products and subtracting from that the heat of formation of the reactants, because we're going to, just like Hess's law, take those products which actually are going to be broken down as opposed to being formed. So we're going to subtract those because we're changing the direction of which those reactions are happening. So here's our reaction. So delta H for our reaction is, again, the products. So we'll add up all the energies associated with the products and subtract from that all the energies of the reactants. And we'll have to multiply for the proper number of moles. So let's take a look at what one of these are going to look like. So here's our reaction of methane and oxygen combusting to make carbon dioxide and water. And I'm going to take my methane and the amount of energy that is to form methane, negative 74.86 kilojoules per mole. And then the same for oxygen, which again, being elemental state, is 0. Carbon dioxide is a negative 393.5 kilojoules per mole. And my water is negative 241.8 kilojoules per mole. So again, I'm just going to take my products, add them up, and subtract from them my reactants, and then that'll give me the overall energy for this reaction. I do need to multiply my oxygen by 2, which is easy because it's already 0, and my water by 2 again because there's 2 moles of water associated in this reaction. So we see our enthalpy for the entire reaction ends up being a negative 802.4 kilojoules, again being released exothermic because it's negative.